Hi all, today we discuss theorem 7.13. So this is also a sufficient condition. We already proved that uniform limit of sequence of continuous functions is continuous. So if we assume this, suppose that K is a compact subset of a metric space. Sequence Fn is a sequence of continuous functions and which converges to a continuous function f on K. In the previous theorem we have assumed the uniform convergence of a sequence of continuous functions and we can get the uniform limit is continuous. In this case we assume that the sequence of continuous function converges to a continuous function. Okay, then does it imply that the convergence is uniform? That's the question here. So that is true if we assume one more, if we impose one more condition here. If the domain is compact and fn of x is greater than or equal to fn plus 1 of x, that is the sequence is decreasing. Okay, so in that case we can get the convergence is uniform. Okay, so this is the theorem. K is compact, fn is a sequence of continuous function and that is also converges to converges to a continuous function f. Okay, we are not aware of the convergence uniformity of its convergence, and we have this result. It is uniform. It is monotonically decreasing sequence. Okay, then we need to prove that fn converges to f uniformly. So to prove this theorem, we need to refer a theorem 2.36 of our textbook. So it says that if K alpha is a collection of or family of compact subsets of a metric space X, such that if we choose any subcollection of this, okay, any finite subcollection of this family, then that intersection is non-empty, implies that the whole intersection is non-empty. Okay, any finite subcollection is in non-empty intersection, then the whole intersection is also non-empty. We use this theorem to prove theorem 7.13. So 7.13 is start with a compact set K and sequence of continuous functions. Okay, so first of all we define a new function for the proof. We define Gn. Gn is defined to be the difference of fn and that f. Okay, that is Gn is equal to fn minus f, but we are given that fn converges to f pointwise. Pointwise convergence is there, so we can say that this Gn converges to 0 pointwise. Okay, we need to prove that this convergence is also uniform. That's the thing. So we need to prove that it is enough to show that Gn converges to 0 uniformly. Okay, Gn of x converges to 0 uniformly. Okay, we are given that this fn is a continuous function, f is a continuous function, so that implies Gn sequence Gn is a sequence of continuous functions. Okay, and Gn converges to 0 as well. So these are the situation here. But one more thing, if we are given that f1 fn is greater than or equal to f2 greater than or equal to f3 and so on, this implies f1 minus f is greater than or equal to f2 minus f is greater than or equal to etc. Okay, so this implies G1 is greater than or equal to G2 is greater than or equal to etc. So that means this Gn is also a sequence of decreasing functions. That means Gn has the same property as this fn have, each f1, f2, f3, f. Okay, so we define Gn, and using this Gn we will prove the uniform continuity of this fn. Okay, so to prove the uniform convergence of this Gn, we start with epsilon greater than 0 and we define Kn. Kn is set of all this x belongs to our domain E, such that Gn of x is greater than or equal to epsilon. Okay, so this is the definition of a new subset of K. So we define it if this X belongs to K, instead of E we have taken K here. So this is our K. So this Kn is a subset of this K such that X belongs to K with Gn of X greater than or equal to epsilon. Okay, but we are given we have already observed that this Gn is continuous. Okay, so therefore this this set can also be written as a Gn inverse of, so this is nothing but G1 inverse of epsilon infinity. Okay, so this is a closed set. This is a closed subset of real numbers. So and Gn is continuous, then inverse image of closed set is again closed. So this implies Kn is closed. Okay, but we know that closed subset of a compact set is compact, so Kn is compact because Kn is a closed subset of a compact set K. Therefore Kn is compact. Now what is the inclusion between K1, K2, K3, etc. Okay, if we consider K1, K2, etc., then we know that if we choose a point X belongs to this Kn, so I write it as some Kn here, so we know that here Gn of X is greater than or equal to epsilon. Okay, but we know that this Gn minus 1 is which is greater than or equal to, this is Gn minus 1. Gn minus 1 of X is greater than or equal to Gn of X greater than or equal to epsilon. Okay, which shows that Gn minus 1 of X is greater than or equal to 0, so that X belongs to Kn minus 1. Okay, what is the relation between this? Whenever X belongs to Kn, then that X belongs to Kn minus 1. Okay, so which implies Kn is a subset of Kn minus 1. Okay, so this K that means K1 is a K2 is a subset of K1, and K3 is a subset of K2, and so on. So this satisfies this inclusion. K1 contains K2, K2 contains K3, K3 contains K4, and so on. Okay, so now we have this Kn is a Kns are collection of compact subsets, compact sets, and we know that Kn satisfies these inclusions. K1 subset of K1 contains K2, that contains K3, that contains K4, and so on. Okay, now we will observe that if we now we can use the reference theorem 2.36. We know that whenever every finite subcollection is non-empty, then the entire intersection is non-empty. Okay, if you consider any intersection of finite subcollection, then if that is non-empty, then we can get this. So what is the contrapositive of this? If K alpha, intersection K alpha, the whole intersection K alpha is empty, implies this finite intersection is, okay, some finite intersection is empty. So this is the contrapositive that we have to use here. Okay, so since this is the case, if we fix an X, let X belongs to this K. Okay, if we fix an X, we know that Gn of X converges to 0 as n tends to infinity. Okay, because Gn of X converges to 0 pointwise. So this implies that Gn of X less than epsilon after a stage. Okay, after this stage we can say that Gn of X is less than epsilon. So this implies X does not belong to Kn onwards. Okay, x, because gn of x is less than epsilon, so that the definition of Kn is gn of x greater than or equal to epsilon. So we can say that corresponding to this gn, g capital N of x is less than epsilon, so x is not an element of that Kn. Okay, so if x not an element of Kn implies, if we fix an x, we can say that x does not belong to some Kn. Okay, so intersection Kn is empty. Okay, so if you fix any x, then there exists n such that x does not belong to n. Okay, no element of this k, or if we set n, if we choose any x belongs to k, then we can see a Kn such that x does not belong to Kn. So we can never expect the intersection contains at least one element. Okay, if this is the case, then we can say that there is a finite collection, intersection which is empty. Okay, so this shows that this implies there exists a finite subcollection, finite intersection of subcollection, finite intersection of a subcollection is empty. Okay, then we can get some kn1, kn2, etc. kn r. This is a finite subcollection whose intersection is empty. Okay, so this is an empty set, so we write it as empty set. Okay, so we know that if we assume n1 greater than n2 greater than etc. nr, then we have what is the intersection of this, that will be knr. Okay, so that is empty. Intersection of all this is knr, because k1 contains k2, that kn1 contains kn2, kn2 contains kn3, and so on. So the largest suffix will be the intersection of all this, so that quantity is empty. So there exists, I put capital N, there exists n such that Kn is empty. What is the meaning of this? Kn is empty means n contains kn plus 1, contains kn plus 2, etc. If this is empty, then these are all subset of this. So we can say that if Kn is empty, then Kn equal to Kn plus 1 equal to etc. Oh, everything is empty. Okay, so which shows that if Kn is empty means what is the definition of this Kn? Kn is x belongs to k such that gn of x is greater than or equal to epsilon. So this is empty means for all x we have gn of x is less than epsilon. Okay, so this is empty means if we can never expect any at least one element of k inside this, that means for all x gn of x is less than epsilon. Okay, similarly for all x gn plus 1 of x is also epsilon, less than epsilon, and so on, because kn is empty, kn plus 1 is empty, etc. So which shows that gn of x is less than epsilon for all x belongs to k and n is greater than or equal to capital N. Okay, which shows that gn of x converges to 0 uniformly, because this is same as gn of x minus 0. Okay, therefore fn converges to f uniformly. Okay, this proves the theorem 7.13. Okay, now we will discuss there is one example after example is discussed in textbook after this theorem, so please go through it. And the next we will discuss theorem 7.14. So that is not theorem 7.14, that is definition 7.14. So using this uniform convergence, we will discuss a connection between norms and this uniform convergence. Okay, so next is a definition 7.14. We write what is the definition 7.14. this is the definition. If X is a metric space, then C of X will denote the set of all complex valued continuous bounded function with domain X. Okay, so what is C of X? C of X consists of a set of all f from X to complex numbers. Okay, such that this f is continuous and bounded functions. Okay, so this is the C of X. So this is the definition of C of X. Now if this is the case, we define a norm f on this C of X, that is supremum. If we choose any f belongs f from C of X, we define this set of all supremum X belongs to X mod f of X. This mod is nothing but the modulus of our complex numbers. So this is f of X is a complex number, so we take complex number f of X and take the supremum of that. So that will defined as supremum norm. This norm is called supremum norm. Okay, so these are two definitions in discussed in 7.14. Now let's see some consequence of this definition. So if we define a norm on the Cx, we know that every normal space is a metric space, because if we define df comma g is equal to norm of f minus g, so this defines a metric. Before that, if you can easily verify that this is a norm, it satisfies all the conditions of norm, that is norm f is always greater than or equal to 0, and norm f equal to 0 if and only if f equal to 0, f is identically 0, and we have norm f plus g less than or equal to norm f plus g, etc. So you can verify all this. I left it as an exercise, so please do it as an exercise. Verify that this is a norm, okay, or it satisfies all the definitions of norm. So now we using this norm, we define this distance. Then using this distance, we can consider C of X is a metric space. Okay, metric space. And if we consider a sequence in this sequence Fn in C of X, okay, if we consider sequence in this, and suppose that the sequence Fn converges to F in the metric space C of X. So what is the meaning of this? That means for every epsilon greater than 0, the distance between Fn comma F is less than epsilon for all n greater than or equal to n. Okay, that is the meaning of the convergence of, or the for epsilon greater than 0 there exists n, such that d of this is less than epsilon for all n greater than or equal to n. That is the definition of the convergence of this metric sequence in this metric space. So what is the meaning of this? For every epsilon greater than 0 there exists n such that, what is d of fn minus f? That is f norm fn minus f less than epsilon for all n greater than or equal to n. So for every epsilon greater than 0 there exists n such that, what is norm of this? That is defined to be supremum x belongs to E fn of x, or no, supremum x belongs to x, not E. Supremum x belongs to x fn of x mod fn of x minus f less than epsilon for all n greater than or equal to n. Okay, so this implies supremum this is defined to be the mn is less than epsilon for all n greater than or equal to n. So that implies mn converges to 0 as n tends to infinity. So that is the meaning of this. Conversely, if you assume this, then you can get this one, and which implies this one, and that implies again so this is if and only if, this is if and only if, and up to all the way up to this. That means if you consider the convergence of this sequence of this metric space is same as the uniform convergence. Okay, if you get the convergence as a sequence in C of x is converges, then with respect to this D or with respect to this norm, then that convergence is in fact uniform convergence. Okay, so that is the consequence of this definition. Okay, so therefore a sequence Fn converges to F with respect to the metric of C of x if and only if Fn converges to F uniformly on X. That is the meaning of these observations. Okay, now accordingly, since this the convergence of, as far as the convergence of sequence and C of x are concerned, we can say that closed subset of C of x are sometimes called uniformly closed. Okay, so that means if we consider let K be a closed subset of C of x is also known as uniformly closed because of this observation, uniformly closed, because the closeness means it contains all its limit points with respect to this D. Okay, that limit points is that convergence is nothing but the uniform convergence. That's why it is called uniformly closed. So those closed subsets are called uniformly closed, and the closure of some subset. Okay, this is the closure of K, and this is also called uniform closure. Okay, uniform closure of K. So these are two terminologies, uniformly closed and uniform closure. So this is because of these observations. Convergence of sequence in C of x with respect to this metric is same as the uniform convergence. Okay, so there is a theorem connecting these two relations, uniform convergence and this norm. So that is theorem 7.15. so we can discuss that theorem. The statement is, this is a statement: C of x is a complete metric space with respect to this metric. Okay, now we'll prove the completeness. So we start with a Cauchy sequence. Let sequence Fn be a Cauchy sequence in C of x. What is the definition of Cauchy sequence? For every epsilon greater than 0, there exists n such that d fn comma fm less than epsilon or less than or equal to epsilon for all n greater than or equal to n for all m greater than or equal to n. So this is the definition of Cauchy sequence. Now this is the distance. Distance is defined to be the norm of fn of x minus fm of x, which is less than or equal to epsilon for all n greater than or equal to n for all m greater than or equal to n. Okay, and again, so from this you can say that supremum of this x belongs to x, fn of x minus fm of x. This is the definition of the norm, which is less than or equal to epsilon for all n greater than or equal to n for all m greater than or equal to n. So this implies if supremum is less than or equal to epsilon, then each quantity is less than or equal to epsilon. So fn of x minus fm of x less than or equal to epsilon for all n greater than or equal to n, for all m greater than or equal to n, and for all x. This is true for every x. This is the Cauchy criterion for the uniform convergence. So this implies fn converges uniformly. Okay, so we can expect a limit function, say fn converges to f, there exists some f, okay, f uniformly. Now we'll prove that this f is in C of x itself. Okay, so that is the idea. So if since this convergence is uniform, and we are given that fn are members of C of x, so fn is continuous. So sequence fn is a sequence of continuous functions. It contains, C of x contains continuous bounded functions. Therefore this f is implies f is a uniform limit of sequence of continuous functions. Okay, by theorem 7.12 you can say that uniform limit of sequence of continuous function is continuous, then f is continuous. Okay, and we know that each fn is bounded as well. Okay, since if we choose n which is greater than n, then we can say that this f of x minus fn of x, if we choose n, okay, we assume that fn converges to f. Therefore every epsilon greater than 0 there exists n such that this is less than epsilon. So we can start with epsilon equal to 1, then there exists some n1. For every n greater than or equal to n1, we have this is less than 1. Okay, because of the uniform convergence. So this implies what is the meaning of this? Minus 1, that is f of fn of x. Fn of x minus 1 less than or equal to f of x less than or equal to fn of x plus 1. Okay, this is true for every x belongs to x. Okay, now we are given that fn of x are elements of c of x, and c of x contains bounded function, so this fn x is bounded. Okay, so we can say that each fn of x is bounded, therefore this mode f of x can be first of all we can write it as from this we can write this as f of x minus 1 modulus of this by adding 1 sorry, this is first of all we write the boundedness of this is fn of x plus 1, and we know that mode fn of x is less than or equal to m, which shows that f of x lies in between m and minus m. Okay, so these are the bounds of f of x, but therefore this can be less than or equal to m plus 1, and this is f of x, and this f of x, the minimum value of this f of x minus m, so this is minus m minus 1, which shows that f is also bounded. Clear? So f is bounded and f is continuous, then f belongs to c of x. Okay, so every Cauchy sequence, if we start with the Cauchy sequence fn, so every Cauchy sequence converges to f which is inside this c of x, which shows that this c of x is complete. Okay, so this proves the theorem. In the next class we will discuss the relation between uniform convergence and integration. Thank you.